Why only 17 joined, ma? Are you able to listen my voice? Arpita, Kavya, Krupa.
Yes, ma'am, you are audible.
Then inform only 17 have joined. I'm waiting, no? Ask them to join fast. Anyone inform, please? Shall I start? Or wait? You want me to wait? It's already 12 o'clock.
Start, ma'am.
Okay, I will start. See, on time you have to join. I have every faculty can't wait, no. Huh? You can join the class. Still one more IA is there. If you don't join and attend the classes, how you will pass? Tell me, what you will write? Join on time to the classes. Don't be delay. Okay, last class what we have discussed? Can anyone tell me? What we discussed last class? Students, what we discussed in the last class? Are you there or not? What is there visible on the screen? Am I audible? Then tell me, what is visible on the screen? Nobody is openly saying. Huh? What is there? Prevention of scales. Correct? Prevention of scales. So now what we will discuss is here today. If you can't see the screen, tell me. I'm unable to see the screen. Are you?
Ma'am, it is prevention of scales visible there.
Okay. It is visible?
Yes, ma'am.
Okay, then okay, fine. So prevention of scales here. So extraction, external treatment includes effluent. External treatment includes efficient softening of water. See, last class we discussed about scales. the formation of boiler corrosion and how scales are formed, and what are its advantages and disadvantages of scales forming, and what are the chemicals involved in the water, boiler feed water involved in the contaminants involved in the water to boiler to undergo boiler corrosion. This is what we discussed in the last class. That is, external treatment includes efficient softening of water, correct? And this is a prevention. How do we prevent the scale? Once you prevent the scale, easily the efficiency of boiler can be improved. This is what we discussed in the last class. Sludge also we discussed. What is sludge? It is a loosely bound precipitate attached to the walls of the surface of the boiler. Because of the boiler feed water contains impurities like magnesium carbonate, magnesium sulfate and calcium chloride. The disadvantages are is poor conductor of heat, reduces efficiency, and sludge need to be removed regularly. This cleaning process is expensive. This is a sludge formation. And next is prevention also we discussed. The next we'll go to priming and foaming. This is not there in your syllabus, priming and foaming. I'll just tell you what is priming and what is foaming. Priming and foaming is, priming you will get in the boiler when it is at a high temperature. You will get rapidly increase in the, you will get the wet steam. Along with the steam you will get water vapors. So this is shows it is a poor efficiency of a boiler. So this boiler, the wet steam generated from the boiler because of the contaminants or impurities, because of boiler corrosion, this is called as priming. Foaming is nothing but from the boiler, if bubbles are generated from the boilers, bubbles are generated from the boilers and do not break very easily. Foaming is due to presence of substances like oils. Because of poor efficiency of boiler, bubbles increases from the, bubbles releases from the water vapor from the boiler. This is called as foaming. All these priming, whether it is a wet steam or a bubbles generated, all this is because of the boiler corrosion, generated due to boiler corrosion. This is priming and foaming. So scales, sludges, the formation of scale and sludge, removal of scale and sludge, and priming and foaming, all are the troubles of boiler corrosion. Boiler corrosion. So what exactly this boiler corrosion? It is a decay or disintegration of boiler material, either due to either from chemical or electrochemical reaction. Remember, it is a decay or disintegration or distraction of the boiler material either by chemical or electrochemical reaction is called as boiler corrosion, is called as boiler corrosion. And the decay of boiler material due to presence of impurities, this decay, whatever the decay or distraction of the walls of the surface of boiler, it is due to the impurities present in the boiler feed water. It is impurities present in the boiler feed water. Corrosion already we studied, right? It is the distraction of the surface of the metal, that is called as corrosion. And this boiler corrosion is due to oxygen, carbon dioxide, which mainly involved in the cause of boiler corrosion, and by dissolving in water forming a weak carbonic acid which attacks a metal in boiler. Oxygen is present in water, reacts with iron and form red iron oxide. This is also iron, because walls are made with the iron, right? Because of contaminants deposits on the surface of a boiler, iron gets converted into red iron or a rust iron. So this red precipitate converts the iron with the undergoes oxidation to give a red iron, which is nothing but that is hydrated ferric oxide ion, which is the rust. We call it as rust. And the corrosion reduces the thickness of the steam and pipe of the metal. So this all boiler corrosion troubles. These are the main causes or affects the boiler to undergo decay and disintegration, which is called as boiler corrosion. Mainly the walls of the boiler get undergoes decay and disintegrated, that is called as boiler corrosion. So the boiler corrosion is a decay of boiler material. See, boiler is made up with iron, right? See, the full boiler metal body is made up with the iron, which is made up with what? Iron. This is made up with iron. So this iron, when it is react with the boiler feed water, which undergoes dissolved oxygen, which contains dissolved oxygen, it forms hydroxide, which is unstable. So this ferrous hydroxide, again when it react with the dissolved oxygen, excess of dissolved oxygen, to give hydrated ferric oxide, which is called as rust. This already we studied in the second chapter, that is corrosion chapter, right? How corrosion happens. Similarly, the boiler is also made up with the steel or iron. That iron react with the dissolved oxygen to give rust. By adding to this a calculated quantity of sodium sulfate. What is sodium sulfate? Na2SO3. This is sodium sulfate. Or hydrazine. Hydrazine is nothing but N2H4. Along with this, if you add calculated amount of sodium sulfate and hydrazine or sodium sulfide, it undergoes the reaction. It reacts with dissolved oxygen to give sodium sulfide. To give sodium sulfide, you can see formation of Na2SO4 from sulfite to sulfate, from hydrazine to sulfate. This is how the boiler corrosion you can remove. How boiler corrosion? See, boiler corrosion by involving dissolved oxygen, it reacts to give rust, which is hydrated ferric oxide. This dissolved oxygen can be removed in the water by adding Na2SO3 and hydrazine. Na2SO3 hydrazine, if you add, this dissolved oxygen which involved in the corrosion easily removed in the form by reacting with sodium sulfate and hydrazine to give sodium sulfate in the form of sulfates. From sulfite to sulfates, hydrazine to sulfate. This is how we can convert dissolved oxygen, or we can stop reacting dissolved oxygen with iron, the walls of the iron of boiler. And the next, corrosion due to dissolved, this is already we studied, and corrosion due to carbon dioxide. If you look at the carbon dioxide, dissolved carbon dioxide present in the boiler feed water, it undergoes decomposition. See, calcium carbonate at a salt. This is a salt, calcium carbonate is present to give calcium carbonate, carbon dioxide and water. Calcium carbonate, carbon dioxide and water. Similarly, if magnesium bicarbonate salt is present, it gives magnesium hydroxide and carbon dioxide, right? So formed, whatever the carbon dioxide formed here in these reactions, we dissolved in water to give carbonic acid. See, this whatever the carbon dioxide liberated or reacted here, it dissolves in water. It dissolves in water and react with water to give carbonic acid, which is a corrosive in nature. This is carbonic acid, H2CO3. So the dissolved oxygen from dissolved carbon dioxide, from where we will get the dissolved carbon dioxide, it is liberated from decomposition of salts like calcium bicarbonate and magnesium bicarbonate. So this calcium bicarbonate and magnesium bicarbonate undergoes decomposition to give calcium carbonate with the liberation of carbon dioxide. The deliberated carbon dioxide at high temperature, this happens, this will dissolve to produce, this will dissolve in water and react with water to give carbon dioxide, which is a slightly acidic and corrosive in nature. So once the carbonic acid is liberated, because of this nature, corrosive nature, the boiler is affected. The efficiency of boiler decreases. And how do you remove this carbon dioxide? And we will see how do you remove. Next, magnesium chloride. This magnesium chloride also, which is one of the contaminant, because of this boiler undergoes corrosion. So when magnesium chloride at a pressure, due to high pressure, which is present in the water, it react when it is feeded in the boiler feed water, that is water, the pH, it drops below 8.5% by forming magnesium hydroxide and liberating HCl. And this is the reaction involved here. How magnesium chloride, if it is present in the water, dissolved form, dissolved water, it how it gives, and it drops the 8 point pH to 8.5. Below 8.5 means it is acidic. So here Fe iron, and when it react with HCl to give ferric chloride, the liberated HCl, whatever HCl is liberated, this HCl reacting with walls of the boiler which contains iron to give ferric chloride, which is unstable. Once the ferric chloride is formed, this react with water to give ferrous hydroxide, which is unstable. Once the ferrous hydroxide is formed, it is easy to convert Fe to O3. It is easy to convert into the form of Fe2O3, which is a hydrated ferric oxide. Fe2O3, which is nothing but the hydrated form, which is nothing but the what is that? Rust, which is called as rust. Once a ferrous hydroxide is formed, easily it can convert it to hydrated ferric oxide, which is called as rust. So because of magnesium chloride and because of carbon dioxide also, it undergoes corrosion. Boilers get affected by the corrosion. Slides are moving. Students? Hello? Anyone respond?
No, ma'am.
Then nobody is saying? You should answer me, right? Huh? I thought it's moving. Till now, what was the last slide you have seen? What is the last slide you saw?
This only,
This
ma'am.
one?
Prevention of scales.
Okay. Now, okay.
Yes, ma'am.
So much I explained and you did not check. Huh? Okay, again I'll repeat. So the boiler corrosion, it is nothing but it is a decay or disintegration of boiler material either due to chemical or electrochemical reaction with its environment. And this disintegration similar to the surface material, how metal surfaces undergo corrosion, same way boilers also undergo corrosion because it is also made up with the steel. It also contains iron. So this, what are the corrosion principles? Corrosion means when it is contains iron, if it contains dissolved oxygen in the water, they react with the walls of the walls of boiler which contains iron. It undergo iron hydroxide, that is ferrous hydroxide. So once the ferrous hydroxide formed, this easily converts into hydrated ferric oxide, which is nothing but rust. Correct? So how do you remove this dissolved oxygen? See, not only dissolved oxygen affects the boiler, also it affects carbon dioxide. We'll see how carbon dioxide. Carbon dioxide means usually water contains salts like bicarbonate, calcium bicarbonate and magnesium bicarbonate, right? So this calcium bicarbonate and magnesium bicarbonate decomposes to give calcium carbonate and magnesium hydroxide with the liberation of carbon dioxide. So this carbon dioxide, when it is in the dissolved form, when it reacts with water to give carbonic acid, which is corrosive in nature. Not only carbon dioxide and oxygen, it also include the effect magnesium chloride. So this magnesium chloride salts, it is present in water in the dissolved form. It reacts with water to give magnesium hydroxide. By forming this, it drops the pH value below 8.5 with the liberation of HCl. So the liberated HCl react with iron to give ferric chloride. Once the ferric chloride formed, this ferric chloride react with H2O dissolved in the dissolved form, converts into unstable iron hydroxide, that is ferrous hydroxide. So once it is formed unstable, then it is easily converts to rust. By forming rust, it decreases the efficiency of boiler. And how do you remove this type of oxygen and carbon dioxide? Oxygen can be removed by treating with sodium sulfite, hydrazine, and sodium sulfide. So when it is removed, when you add a calculated quantity of these three, the dissolved oxygen present in the water to combine to give sodium sulfide, sodium sulfate, and nitrogen and sodium sulfate. So by converting into other form of salts, you can easily remove dissolved oxygen. Similarly, if you want to remove dissolved carbon dioxide, when you add limestone contains calcium carbonate, right? So when you add this calcium carbonate to water, dissolved water in calculated quantity of calcium carbonate, whatever the dissolved carbon dioxide present in water combines, it gives calcium bicarbonate. So if by converting calcium carbonate to calcium bicarbonate, easily you can remove the carbon dioxide. Not only calcium carbonate limestone, it can also removed by adding calculated amount of ammonium hydroxide, that is NH4OH. When you add NH4OH with carbon dioxide, it gives sodium carbonate. It gives sodium carbonate, that is finally acidic impurities. Sodium carbonate, it liberates. So this sodium carbonate, this is how we can remove the oxygen and also carbon dioxide. So how do you prevent? Prevent by deaerator method. And prevent by deaerator method means, see, before feeding the water into the boiler, see, the water, before this water feeding into the boiler, take into a device which contains, this is a device, this device has water storage section where you can store the water, and once you heat at high temperature, the dissolved salts, the impurities, everything settles here in the storage tank, and pure water with water vapor settles at the top portion. Once this top portion vapors are settles here, easily it can be taken out from the air vent gap, and which is collected, and it can be used in the boiler feed. You can, that water which is being collected at the top portion of this device, it can be used in the boiler, which can be as a boiler feed water. To help this, we have a pump which is deaerated, boiler which is deaerated, remove the water. So this device is called as deaerator. Deaerator means by removing the impurities by heating at high temperature, which is a horizontal tray shaped device. It can be easily remove the salts and dissolved oxygen gases, whatever it is present in the from the water. After dissolving, after removing from this, it can be easily taken out from the top section of the top portion of this deaerator, which is by this you can prevent boiler corrosion by feeding this type of water into the boiler. So, understood? Anything you want to repeat in the boiler corrosion? What question you are expecting from here is, you can expect two type of questions here. What are boiler corrosion, or explain the boiler troubles, And how do you remove boiler corrosion? Removal of oxygen and carbon dioxide. One question. Or explain the process of boiler corrosion. And how do you prevent the boiler corrosion? This is one question you can expect from this boiler corrosion chapter, topic. So after this, we have another subtopic which is COD, that is chemical oxygen demand. Can we, shall I move to the next topic or you want to repeat it? Anything you want to repeat? Which point you did not understand? Students? Are you there?
Yes, ma'am. Go for the next topic, ma'am.
Shall I move? No doubts here? You want to repeat anything?
No, ma'am.
Huh?
Go to the next topic.
No, ma'am.
Okay, I'll go to the next. Next is COD. If you have any doubt, you can ask me. Okay. COD is nothing but chemical oxygen demand. I think we showed you this experiment in the when you have come for practical classes, right? The COD you have done in the practical. COD experiment. COD is nothing but chemical oxygen demand. This chemical oxygen demand, the same experiment you have done in the practical also. What is this definition? It is defined as the amount of oxygen is required. What is the COD? How much amount of oxygen is required for the complete oxidation of both organic and inorganic matter. Say suppose if water contains both organic and inorganic matter, how much oxygen is required to oxidize this organic and inorganic impurities present in water. Such type of oxidation are used called as strong by using strong any oxidizing to if it is undergoing oxidation means we need an oxidizing agent, right? So by using oxidizing agent, if you are oxidizing this organic and inorganic matter, how much amount of oxygen is required to undergo this oxidation, that is calculation is called as COD. From where you are calculating this? From the 1 liter of wastewater. So what is the correct definition? It is defined as amount of oxygen required for the complete oxidation of both organic and inorganic matter present in 1 liter of wastewater using strong oxidizing agent. This is COD definition. What is the principle involved here? It is a method. It is a method by containing, like we are containing, consider a sample of water contains both organic and inorganic impurities. Okay. By what is oxidizing agent we are using? K2Cr2O7, potassium dichromate. This is the oxidizing agent. By using this oxidizing agent, we oxidize this both organic and inorganic. And once it is oxidizes, again it is how it get oxidizes by titrating against FAS. You can easily calculate how much amount is required, how much amount of potassium dichromate is required to undergo oxidation. What type of reaction it is? It is a type of reaction involved here is redox reaction. Why it is called as redox reaction? Because potassium dichromate is oxidizing agent, and FAS we are using as reducing agent. Here we use indicator which is called as redox indicator, which is the name of the indicator is ferroin. Name of the indicator is ferroin. So by using this indicator ferroin, you can see the change in the color. You can see the change in the color once all the organic and inorganic impurities get oxidizes. What is that color change? It changes from bluish green to reddish brown. I showed you the formation of this bluish green to reddish brown, right, in the practical classes. How many of you have observed? We have showed you the demo, right? COD experiment. Remembered?
Yes, ma'am.
Yes, the same experiment here. So what is the principle involved here? The principle is mainly we are calculating how much oxygen is required to oxidize these organic and inorganic impurities by using oxidizing and reducing agent. So what is required here from the burette? In the burette we take standard FAS as a reducing agent, and H2SO4 we are taking as to dilute up to the marker. So take a known quantity of FAS in the standard flask, transfer it, add H2SO4, prepare the standard solution and fill in the burette. That is the burette solution. In the conical flask, this is called as back titration. You have to pipette out 25 ml. Usually we take it as 25 ml of wastewater we are pipetting out. That 25 ml of wastewater, and usually here we pipette out 10 ml of potassium dichromate and 10 ml of H2SO. Usually one test tube of H2SO4 we take and 1 gram of AgSO4. Why AgSO4 is required? Because it acts as a catalyst which boosts the reaction, redox reaction, but it does not involve in the reaction. So this is the catalyst what we are taking, that is AgSO4 as a catalyst, followed by HgSO4. HgSO4 is mercuric sulfate, and then 2 to 3 drops of ferroin indicator. Add 2 to 3 drops of ferroin indicator, titrate against FAS. This is the conical flask solution. This is called as back titration. What is blank titration? Blank titration, similar to this titration, we are doing the back titration by taking 25 ml of distilled water. So how much oxidizable impurities are present in distilled water? We are calculating, that is the blank titration. After that, tabulate all the reaction, all the quantity and substitute in the equation, that is n. Find out the normality here. Normality you are adding. B2 is back titration, blank titration minus back titration. What is a tabular column? That is the burette reading value into 8000 divided by volume of water sample. Usually it is 25 ml. How much we pipette out, that much we have pipette. Substitute in the equation and calculate this. After substituting it is, we will get how many milligrams of oxygen is required per liter. What is N here? N is the prepared normality of FAS solution. V1 is volume of FAS consumed. V2 is volume of FAS consumed for blank titration. This is how we do COD. We calculate how much oxygen is required for the oxidation. Understood? And based on this, it's not only COD, we use BOD also. See, similarly, COD is what? By using chemicals. BOD is, it is a biological oxygen oxidation. The amount of oxygen required for biologically oxidation by using whatever the oxidizable impurities are present in wastewater under aerobic conditions over a period of 5 days to 20 days at 20 degrees Celsius. It is undergo biological oxidation by involving microorganisms, and it undergo aerobic condition. It has been calculated in terms of BOD, which is called as BOD, and this BOD is also expressed in terms of milligrams per dm cube. So COD is by using chemical reagents, BOD is by using biological oxidation. So based on this COD and BOD, we will calculate we will do some problems in the exam or in the IA. I will ask you to calculate. There is equations are there. You have to solve some problems. COD, come attend the class tomorrow with calculator. We do some numericals. on COD. Clear? Answer attended 63. Answer your attendance 63. 63. 64.
Present, ma'am.